Hello, fellows. I am Dr. Tanisha Wright. Welcome to today's lecture on the foundations of quantum machine learning. I'm delighted to be guiding you all through this lecture. As Benjamin Franklin once said, "Tell me and I forget, teach me and I remember, involve me and I learn." My aim is to thoroughly involve you all so that you all deeply learn the core concepts. We'll begin by briefly reviewing some key ideas from classical machine learning, setting the stage for our quantum journey ahead. Machine learning utilizes statistical models and algorithms to analyze and draw insights from data without being explicitly programmed for specific tasks. Through exposure to many examples, models discern intricate patterns, enabling them to make predictions or decisions. Consider spam filters. They aren't directly coded to identify spam, but rather they statistically learn based on seeing many emails. A model's architecture defines its core components and how they interact. For instance, neural networks have layers of interconnected nodes, like biological neurons. Architectures can range from simple linear models to complex multi-layer neural networks with millions of parameters. Models also have associated training algorithms that iteratively update parameters to optimize performance on training data. Additional procedures assess accuracy on new unseen data. So in summary, architects design model blueprints, training algorithms build by remodeling parameters, and validation checks quality. With the rise of big data, machine learning has become essential for tackling complex real-world problems. However, hunger for ever larger models strains even the mightiest computing hardware. Quantum computing promises breakthroughs in processing power to take machine learning further. Transitioning to quantum, we enter an exhilarating new paradigm underpinned by quantum physics. Rather than binary bits, quantum computers harness qubits, which exploit superposition and entanglement. While a bit encodes 0 or 1, a qubit can represent a combination, enabling exponentially more information density. Furthermore, entangled qubits exhibit spooky coordinated behavior, unlike anything classical. Leveraging these quantum advantages for machine learning gives birth to the vibrant new field of quantum machine learning. QML interleaves both quantum and classical resources. We distinguish quantum machine learning models which run primarily on quantum devices from classical models enhanced with quantum subroutines. An example of the latter is using quantum algorithms for optimization tasks, like tuning model hyperparameters. Meanwhile, true QML models might have qubit layers intrinsically woven into their architecture. We will thoroughly cover techniques for constructing quantum layers like variational circuits and integrating them into neural network designs. Furthermore, we will discuss tailored training procedures leveraging quantum optimization to update parameters. We'll also address evaluating model accuracy and benchmarking performance relative to classical counterparts. Across application domains like computer vision, natural language processing, recommendation systems, and more, we will highlight practical QML innovations. By this lecture's end, you will grasp the foundational concepts fueling this quantum learning revolution. You will understand how to build, train, and validate integrations of quantum and classical resources for machine learning. Through ample examples and hands-on code, you will gain intuitions for where quantum advantages can manifest. So, buckle up, students. Our quantum future awaits. Now let's dive deeper into the machine learning preliminaries underpinning our quantum journey. Earlier, we introduced core machine learning concepts. Now let's go deeper. Consider model training. The goal is optimizing parameters to minimize a loss function that quantifies prediction errors on training data. This enables accurately generalizing to new data. Loss functions vary across problems. For classification tasks, common choices are cross-entropy and hinge losses. Regression problems often use mean-squared error. Training loops through datasets in batches, making prediction, assessing loss, then tweaking parameters via gradients to reduce errors. Batching chunks data for efficiency over iterating individual samples. Batch size tunes the optimization. Too small, and noise obscures useful learning signal. Too large, and computation lags. Batching also shuffles data to smooth updates. Speaking of optimization, let's contrast two prevailing techniques. Classical stochastic gradient descent starts with random parameters, determining gradients on each batch to iterate toward better regions. In contrast, quantum variational algorithms parameterize the model as a quantum circuit, exploiting quantum evolution to find optimal values. We'll thoroughly cover both methodologies. Welcome, students. In this lecture, we will review core concepts in the vast world of machine learning, laying foundations for our quantum journey ahead. If you have existing ML experience, feel free to tune out the basics. For true beginners, get ready to have your mind expanded. Machine learning aims to create algorithms that can analyze data patterns without explicit programming. Through seeing numerous examples, models discern intricate structures and rules. This knowledge enables them to make predictions, decisions, and generate novel synthetic data. Consider the goal of designing a system to classify images as either cats or rabbits. Traditional code would painstakingly define visual rules, distinguishing the two. But machine learning takes a radically different approach. Showing the system many labeled images, it statistically learns the separating features itself. Intricate discriminating patterns emerge from data, not hard-coded constraints. We call such a system that assigns categories a classifier. For binary cases with two possible labels, classifiers are termed positive or negative examples. Beyond cats versus rabbits, classifiers address endless real-world challenges, identifying diseased medical scans, labeling suspicious transactions as fraud, detecting network intrusions, and vastly more. Through this broad applicability to pattern recognition, machine learning now permeates science and industry. Architecting such adaptive intelligence systems requires core components. First, we need a predictive model defined by an architecture with adjustable parameters. This acts analogous to the brain holding knowledge in synaptic connection strengths. Architectures range from simple linear classifiers to elaborate multi-layer neural networks. Next, we need a training algorithm that uses data to tune parameters, optimizing model performance. This mimics learning through experience, gradually molding brain wiring. Finally, we evaluate accuracy on new test data. Together, this generates a feedback loop. Data enables model adaptations through training to improve predictions, rinse and repeat. Mathematically, we frame this as minimizing a loss function that quantifies errors on training data. Optimization iteratively adjusts parameters along gradients descending toward values with lower losses. Batching randomly samples subsets of data to smooth the ride. Eventually, models converge to a sweet spot, generalizing well to unseen data. The goal. While easy to state at a high level, implementation details determine success. Choices in model architecture, optimization techniques, regularization methods to prevent overfitting, and more constitute an art honed through diligent practice. Fortunately, powerful frameworks like TensorFlow radically simplify experimentation, putting these tools in your hands through coding interfaces. Later, we will demonstrate basics, but first quantum calls, onward. Now that you appreciate the essence of machine learning, we can import these principles into the quantum realm. Quantum physics introduces radical new dimensions with exponentially larger state spaces through superposition, exponentially faster processing via quantum parallelism, and entanglement enabling non-local correlations. This enlarges the machine learning playground. Quantum machine learning aims to exploit such quantum advantages for superior statistical modeling over classical. We will methodically unpack techniques across supervised classification and regression, unsupervised learning like clustering, density estimation and dimensionality reduction, and reinforcement learning for agents optimizing behaviors. You will gain intuitions for where quantum speedups manifest and how to integrate quantum components into classical pipelines. By journey's end, you will be ready to architect next-generation quantum machine intelligence. But before running, let's solidify foundations. So back to classical ML we go. Our discussion centers on an issue of rapidly accelerating importance in the tech world, leveraging quantum advances for more powerful and efficient machine learning. As data generation scales exponentially, even the mightiest supercomputers struggle analyzing data sets, now frequently exceeding petabytes and exabytes in size. Moore's law seems to have met its match. Single processors simply cannot keep pace. Parallel computing helps, allowing computations to be distributed across nodes working in tandem, but even massive server farms have limitations. Quantum computing introduces radically new physics, with essentially unlimited upsides for information processing and storage density. Harnessing quantum effects like superposition and entanglement can blow existing algorithms out of the water in terms of speed, efficiency, and scalability. This begs our central question: how can we integrate the principles of quantum computing into machine learning to meet surging big data demands? By retooling classical ML approaches To exploit quantum advantage, we can accelerate training, slash energy consumption, and enhance predictive prowess. Quantum machine learning, or QML, interweaves both quantum and classical resources in complementary ways. Quantum neural networks weave qubit blocks into computational graph architectures for improved representation learning and parameter optimization. Quantum kernel methods leverage qubit inner products for pattern recognition within extremely high-dimensional Hilbert spaces. Hybrid schemes utilize quantum subroutines to boost specific classical bottlenecks. Across methodologies, accurately quantifying runtime and efficiency gains over classical baselines remains an area of active research as quantum hardware rapidly advances. Additionally, quantum information inherently incorporates more robust privacy and security protections than vulnerable classical data. Exploiting quantum strangeness can help future-proof machine learning algorithms against advancing adversarial threats from bad actors. By encoding information within QML models using subspaces of entangled qubits, sensitive personal or commercial data can strongly resist unauthorized access or theft, even by quantum computers. Having encryption keys stored within qubits themselves provides inherent security advantages over classical techniques. With great data, analytics power comes great responsibility. Quantum computing offers breakthrough machine learning capabilities while better safeguarding proprietary data assets and user privacy. Of course, substantial obstacles remain translating quantum theories into practical large-scale implementations rivaling state-of-the-art classical benchmarks. Real-world noise introducing errors must become dramatically lower. As well, efficiently embedding information into exotic quantum data structures and subsequently extracting meaningful classical outputs introduces daunting algorithmic hurdles. Transitioning quantum machine learning beyond contrived toy demonstrations into real deployed systems is no small feat. Yet the staggering potential upside fuels relentless progress. By marrying the statistical learning prowess of AI with the informational density advantages of quantum physics, the future looks inexorably quantum. With diligent cross-disciplinary collaboration spanning computer science, applied physics, mathematics, and engineering, quantum machine learning advanced hybrid systems could soon depart the realm of science fiction and become scientific reality. The mathematical abstractions exist. Now turning equations into functioning QML applications remains paramount. So in summary, students, integrating quantum computing principles into machine learning holds revolutionary promise, addressing imminent big data processing bottlenecks while fortifying security and privacy. Substantial scientific obstacles remain translating theories into practical AI, but pioneers continue pushing boundaries daily. Quantum is the future, so let's equip you to lead this integration. Our journey into the world of machine learning begins by breaking down its fundamental ingredients. First and foremost, we require a computational model powerful enough to tackle our desired predictive tasks. By this, we mean an algorithm that can be configured to solve problems with varying levels of accuracy. Models range from simple linear classifiers to elaborate multi-layer neural networks. For example, perceptrons constitute the basic building blocks underpinning more advanced neural networks. A perceptron takes numerical inputs, multiplies them by adjustable weights, sums them, and thresholds the result to output 0 or 1. By tuning weights, even this humble model can tackle binary classification challenges. Now, a model alone cannot learn patterns. We need data, and lots of it. Real-world datasets get transformed into numerical feature vectors, commonly called attributes, which serve as model inputs. Representing complex phenomena by numbers in this way allows computational analysis. More data exposes intricate structures within high-dimensional spaces. Finally, we need a training procedure to configure models by identifying key data patterns, rather than manually programming analytic rules. We formalize this as an optimization process, seeking parameters that minimize a loss function, quantifying prediction error on training examples. Stochastic gradient descent offers perhaps the most popular approach, iteratively descending toward valleys of lower error. By combining trainable models with sizable numeric datasets and optimization routines, machine learning emerges. The trained model generalizes by capturing core latent data structures, rather than memorizing peculiarities of specific training examples. Assessing performance on unseen test data checks this vital capability. This framework enables learning algorithms to tackle diverse predictive challenges fueled by floods of data. However, concerns accompany proliferating automation. Models amplified to global scales can secretly inherit and propagate societal biases if relying on narrow demographic data. Feedback loops steadily reinforce prejudice. Furthermore, black box complexity obscures accountability, jeopardizing rights. So in a world with exponentially increasing data complexity and ethical considerations, how can we develop machine learning models that not only adapt to diverse dynamic data landscapes, but also maintain fairness, transparency, and accountability in their learning processes? The key rests in promoting not just predictive power, but also interpretability and inclusiveness. Architecting layered explainable models sheds light on decision-making. Actively sourcing representative data and benchmarks mitigates unfair bias. Quantifying uncertainty bounds temper overconfidence. Together, this crafts adaptable and ethical systems poised to uplift society. The challenges ahead demand cross-disciplinary collaboration between social scientists, computer scientists, lawmakers, and domain experts across industries. Only by holistically aligning emerging technologies with human values can we cultivate responsible progress. Our models must mirror the complexity of humankind. This begins with promoting diversity, equity, and inclusion within research teams themselves. So let us embrace complexity of both data and people, shaping machines that empower. Now that we have touched on core ingredients and challenges, let us dig deeper into computational models and training algorithms driving modern machine learning. We will dig into perceptrons, simple yet foundational models underlying modern deep learning. Perceptrons operate as basic binary classifiers, processing numerical inputs and thresholding weighted sums to output 0 or 1 predictions. Despite their superficial simplicity, perceptrons hold rich historical significance, while also illuminating inherent limitations, motivating ongoing machine learning innovation. Specifically, a perceptron takes n input values x1 through xn, each associated with a weight wi. An additional bias term b shifts classification. The perceptron sums the weighted inputs, sigma over I from 1 to n of xi, wi, and adds the bias b. If this aggregate exceeds 0, the perceptron outputs a 1, otherwise outputting 0. So while very basic computationally, by tuning the weights wi and bias b based on training examples, perceptrons can learn to separating binary classes, given points belonging to one class with output 1 and points of another class with output 0, we can search for coefficients correctly classifying both groups. An effective choice exists provided the data is linearly separable. That is, some linear weight input hyperplane divides the classes. As one of the first trainable binary classifier models, perceptrons hold towering historical importance, launching the rich field of neural networks and deep learning. Yet, as we shall see, their constraints highlight motivations driving ongoing machine learning innovation. While proficient for basic tasks, complex real-world data often defies tidy linear separation. Problems lacking such intrinsic linear structure cause even optimally tuned perceptrons to fail. This limitation manifests concretely in the classic XOR logic operation. Given binary inputs of 0, 2, and 1.1 with output 0, and inputs 0, 1, and 1.0 having output 1, no perceptron configuration correctly implements XOR. We cannot linearly separate inputs needing nonlinear coordination, highlighting the pressing need for more powerful nonlinear models in machine learning. While crucial foundations, perceptrons alone cannot handle the diversity and intricacy of real-world data. Progress compels us to seek improved representations spanning nonlinear spaces, while also advancing interpretable models built on trust and transparency. Only by upholding rigorous benchmarks and ethical standards as we scale can we ensure responsible progress. So, in summary, perceptrons constitute primitive binary classifiers that cannot solve complex problems requiring nonlinear reasoning. By revealing inherent limitations in even foundational methods, perceptrons underscore the perpetual need for better models and algorithms as we pursue general artificial intelligence. More data and compute alone cannot redeem inadequate representations. The journey necessitates consistent innovation. Next, we will build on humble perceptron origins, introducing nonlinear activations and multilayer abstractions, giving rise to the versatile class of neural networks dominating today's machine learning landscape. By stacking representations, we gain expressive might. So onward and upward we go. We saw how linear perceptrons falter trying to model problems requiring nonlinear reasoning. The key breakthrough enabling modeling complex phenomena lay in introducing nonlinear activation functions within neurons. Rather than directly outputting weighted sums, we first squash values through nonlinear transformations, like the classic sigmoid nonlinearity. Mathematically, this activates a neuron's preactivation U to output FU for some fixed nonlinear function as the F. Common choices for F include sigmoids, squashing into 0, 0, 1, tan bounding between 1 plus 1, and Rieloff's thresholding at 0 via FU, I say max 0, U. Even this simple change from purely linear units dramatically expands expressive capacity. Furthermore, by chaining many such nonlinear neurons in multilayer networks, we gain ability to iteratively build up higher-level features, combining simpler representations from below. Intricate hierarchical networks compose distributed computations, far exceeding constituent components. The breakthrough backpropagation algorithm efficiently trains parameters across multi-layer stacks by sequentially attributing credit via the chain rule. Information flows forward inferring predictions, with errors recursively flowing backwards, tweaking parameters layer by layer, iterating gradient descent through backpropagation molds, flexible networks to remarkable effect. We will explore the pivotal machine learning challenge of overfitting, illuminated by a striking diagram. This graphic illustrates overtuning models to training data, compromising generalization. Let's walk through the key elements, reflecting on causes, consequences, and potential remedies to overfitting along our machine learning journey. We see two datasets, training in orange and test in blue, each with scattered points. A polynomial curve snakes through the orange dots, matching them perfectly. This tight fit comes at a cost, however, with the curve deviating severely from the linear trend of the test set and black line marking the true underlying pattern. By tuning so precisely to training intricacies, the polynomial function forfeits generalizability. Its fluctuating shape contradicts the real model, while missing test points that should lie upon the line if learned properly. This divergence between training and test performance signals overfitting. Note the uneven distribution of orange points, with similar x values having varying y values. Such noise encourages the polynomial's twisting attempts, modeling random blips rather than fundamental trends. With complexity outpacing available signal within finite noisy training samples, distraction ensues. Yet given infinite data, noise averages out revealing coherent patterns to model simply without over-contorting. So limited training data partially explains overfitting by providing an unrepresentative, misleading snapshot. But we also cannot disregard the polynomial function's inherent flexibility to wiggle arbitrarily. In machine learning terminology, overfitting arises from having too powerful models relative to too little data. Their extreme capacity to latch onto details enables seductive excellence on training distributions, without sufficiently learning generalizable knowledge to apply broadly. Resisting such temptation proves essential for practical progress. If you suspect overfitting, first seek more training data, allowing simpler models to extract fundamental wisdom rather than hallucinating ghosts and noise. Additionally, directly restraining model complexity by reducing size or simplifying architecture helps bias learning toward generalizable patterns. We must balance power against restraint for reliable knowledge. So in summary, overfitting teaches virtues of gathering abundant data and practicing principled parsimony in modeling. By studying pitfalls like these encountered along the machine learning journey, we gain wisdom to advance further. The road ahead remains long, but vigilance will guide us. Now let us explore productive remedies and best practices to get back on track when veering toward overfitting. The lecture can continue covering techniques like regularization, dropout, early stopping, and cross-validation to help address overfitting. Let me know if you would like me to expand on applying any of those methods. Regularization offers one powerful approach, constraining models by penalizing excessively complex behavior, such as extreme parameter values. We add a regularization term to the loss function that grows with the model's elaborate contortions on training data. This provides incentives toward well-generalizable simplicity. Different regularization variants exist. L1 normalization punishes absolute parameter size. L2 squares values penalizing large outliers, and ElasticNet combines both. By tuning regularization strength, we balance fitting training data against focus for core trends. Too little, overfitting persists. Too much, underfitting arises. Dropout provides another regularization technique, randomly omitting subsets of neuron outputs during training iterations using probability P like Bayesian model averaging. This stochastic noise injection compels redundancy, avoiding over-reliance on specific neurons. Prediction averages across submodels. We also have early stopped, monitoring validation performance over training time. Once metrics plateau or degrade, we terminate before overtuning. However, stopping criteria and checkpoint frequency introduce new hyperparameters. Finally, cross-validation better assesses model generalization by partitioning training data into segments, each taking turns, held out for evaluation. This less biased estimate then guides hyperparameter optimization. Cross-validation couples naturally with early stopping for regularized iterative improvement. By incorporating such techniques as needed given data limitations, we rein in overzealous models, prevent distraction by noise, and better estimate real-world performance. Regularization in its varied forms offers a crucial lever-balancing model power against stability, opening doors for responsible application. On we march. Now that we have thoroughly explored the prominent peril of overfitting, leading models astray, chasing noisy ghosts within limited training data, let us contrast an equally troublesome adversary, underfitting. While overfitting distracts with details, underfitting loses the forest for the trees by missing core structural essence within datasets. We must craft models with appropriate capacity to extract salient signals, neither under nor overshooting mark. Underfitting manifests in high error rates, persisting through both training and testing data. This signal lacking model complexity to represent dataset intricacies. Consider attempting to fit scattered data, tracing a parabolic curve using only a straight line. Severely bounded expressiveness forgoes necessary nonlinearity. Substantial deviations endure across the board. Underfitting models essentially remain blind to embedded trends, lacking capacity to match complexity within datasets. Linear functions cannot latch onto quadratic patterns. Single-layer perceptrons miss intricacies, demanding multi-layer neural networks. Nearest neighbors struggle broadening across high-dimensional manifolds. Such extensive errors on the very data used for training indicates missing core ideas. Solutions demand expanding model representation power and architecture to better match underlying dataset characteristics. We must sculpt appropriately expressive shapes, aligning with true trends. Smooth nonlinear data compels nonlinear models. Broad datasets need highly parameterized functions. Simply put, undermine underfitting through enhanced model competence, strengthen sufficiently to grasp key data structures. Balancing model power underscores an ongoing tension throughout machine learning, echoing our preceding discussion of overfitting's relationship with complexity. Underpowered and we underfit, unable to perceive signal within noisy data. Overpowered and we overfit, hallucinating ghosts from noise lacking external validation. The essential quest seeks sufficient structure to distill insight without inventing fictions devoid of evidence. Regularization further enables managing model complexity, preventing both under and over extremes. We must carefully tune regularization hyperparameters, assessing impacts on training and validation performance. Finding the sweet spot, granting the perfect dose of inductive bias, remains more art than science, but promises ample rewards when harassed by such problems. So, in summary, calibrate model freedom to resonate with dataset complexity, and train with weight clipping when struggling with underfitting or overfitting. Seek representations matching patterns, not imaginations. Choose flexibility fit for purpose. And now with wiser model selection, onwards we march. Model architects face an infinitude of possibilities, configuring optimal structures best resonating with application domains. Mastering this intricate balancing act proves essential. We refer to such architectural variables as hyperparameters, distinguishing them from parameters directly learned from data during training. Hyperparameters exist above data-driven optimization, embedding inductive biases, establishing foundational modeling assumptions and constraints. They constitute the fundamental scaffolding erected to guide the direction of learning. Consider hyperparameters like neural network depth determining layers, width setting node counts per layer, weight initialization seeding connection, strength variation, dropout probability, randomly emitting neurons, and learning rate governing gradient descent velocity. Together, these top-level selections coordinate overall model behavior and complexity. Ideally, hyperparameters harmonize to produce accurate and generalizable statistical models, rapid convergence during training, and computational efficiency scaling elegantly. However, high-dimensional configuration spaces riddle optimization landscapes with perils like underfitting, overfitting, vanishing gradients, and beyond. Finding benign sweet spots within this labyrinth requires almost alchemical mastery. Best practice entails assessing numerous configurations through iterative trials to uncover ideal synergies suitable for particular data distributions and infrastructures. We conduct hyperparameter sweep tournaments, evaluating candidate models by accuracy and efficiency metrics on validation data. Survivors advance generations honing elite performance on core benchmarks. While compulsory for progress, competitive leaderboard chasing alone risk blind spots. Solutions narrowly overfit to popular datasets may exploit incidental patterns rather than robust principles transferable to varied applications. True generality requires human discernment, recognizing what advances the state of the art for the right reasons through ground truth understanding, not mere benchmark gaming devoid of external validity. So, in closing, model selection demands meticulous tuning of hyperparameters balancing accuracy, generalization, interpretability, and computational constraints for responsible machine learning. By acknowledging papers and benchmarks only partially indicate real progress, we see the bigger picture. Onward to tune models resonating with both data and domain wisdom. That is the path ahead. Now let us dive deeper into common hyperparameter optimization strategies and best practices. Grid search provides the most straightforward hyperparameter sweep approach, systematically traversing a predefined sparse grid of settings. All combinations get evaluated in a brute force fashion. Exponential costs quickly become prohibitive for higher dimensions, however. Random search improves efficiency by sampling configurations randomly from predefined distributions rather than regular grids. Performance generally meets or exceeds grid search thanks to broad coverage. The stochastic element also allows budget-limited iteration. Bayesian optimization builds surrogate models predicting performance as a function of hyperparameters to guide intelligent adaptive sampling. By incorporating priors and estimating uncertainty, new promising regions efficiently get identified and incorporated iteratively. However, assumptions may bias search trajectories. Gradient-based optimization directly computes hyperparameter gradients on validation metrics through techniques like reverse mode differentiation. This enables gradient descent efficiently through high-dimensional configuration spaces. Challenges arise from non-differentiable spaces and computational graphs disconnecting across meta-layer boundaries. Population-based methods like evolutionary algorithms apply genetic variation and selection pressures across generations of hyperparameter settings, key to validation fitness. Multiple candidates evolve in parallel guided by fitness rather than gradients. Defining sensible mutation strategies poses difficulties. As you can see, extensive tooling exists addressing hyperparameter optimization, each with unique strengths and weaknesses. In practice, combinations work best. Global stochastic searches to nail down regions of interest. Local gradient adjustments to precisely. We shine light on an unsung hero enabling rigorous machine learning model tuning, the validation dataset. This independent data parcel critically guides selection among model contenders, evaluates preliminary performance to direct improvement, and preserves test integrity for final evaluation. Let us appreciate the instrumental validation set. In partitioning overall data into training, validation, and test subsets, we must establish strict separation to prevent information leakage that could enable cheating. Training data tunes parameters, test data provides final, unbiased evaluation of real-world fitness, and validation data fills the gap, assessing preliminary models to steer constructive tweaking toward excellence. With so many potential model configurations and hyperparameters to explore, how can we efficiently navigate this labyrinth without overfitting on testing data? By introducing an intermediate validation dataset for preliminary model battles. We train candidates on training data, assess preliminary quality on the validation set, then advance top survivors for final testing. This validation assessment enables safely judging hyperparameter configurations and model types, slicing through the dense fog of possibilities. It serves as proving ground and filter, determining which embryonic architectures show promise versus those floundering. We leverage validation accuracy for preliminary model ranking and selection. Top survivors then undergo retraining, unified with the validation data itself to further tune parameters, enriched by increased examples. No dataset goes unused. This final merging and training infusion produces our ultimate champion model architecture. Only then do we unlock the guarded test data to produce our unbiased accuracy estimate confirming generalizability. So in summary, rather than directly flaunting options on testing data, we evaluate preliminary builds on validation data, instead to efficiently guide improvement while preserving test purity for final verification. Validation shepherds models through seasons of iterative refinement toward excelling in their future application environment. It is the engine quietly driving much progress, so let us give thanks to the validation set. Now that we appreciate this key aspect of the machine learning pipeline, let us next explore the powerful practice of cross-validation. While a fixed validation split provides preliminary evaluation, results can depend heavily on randomness in exactly which data points end up in validation rather than training. Cross-validation seeks to overcome this variability, systematically testing models on different subsets. The approach partitions training data into K-equal folds. Then K-separate training runs occur, each picking a different fold to act as the validation set while training on all other folds. We compute validation metrics for every run, then average to reduce noise and better estimate model generalization. In this fashion, cross-validation solicits multiple second opinions rather than trusting a single, potentially arbitrary validation split. And by cycling different folds for validation, all data contributes across assessments, providing a more reliable aggregate measure, zeroing in on true expected accuracy. One complication involves selecting the number of folds, K. More folds reduce variance, but increase computational training costs by a factor of K. Typical values for K range from 5 to 10, balancing stability against budget. But even leave one out with K equal to the number of data points proves popular for small data sets. Model selection, hyperparameter tuning, and early stopping all integrate seamlessly with cross-validation procedures to boost robustness. The ensemble estimates guides advancement of generations of iteratively improving models through successive seasons of training across diverse validation splits. In closing, cross-validation, delivers a more accurate assessment of real-world model generalizability by soliciting multiple opinions, averaging away variability. This enables raising reliability and stability for responsible machine learning. Onwards we march.